Hello and welcome to Portable Stimulus, what's coming in 2.0 and what it means for you. For the next 90 minutes or so, my colleagues and I from the Accellera Portable Stimulus Working Group will be sharing with you some of the new features we've been working on for version 2.0 of the Portable Stimulus Standard, commonly referred to as PSS. I'm Tom Fitzpatrick of Mentor Siemens Business and also the Vice Chair of the Working Group, and I'll be doing a brief overview of PSS, showing you the basics of a PSS model and using a DMA controller as a small example. Then Adnan and Hamid from Breker will introduce the new memory allocation features in PSS 2.0, followed by Matan of Cadence, who will show some new constructs we've added to the language to support modeling higher-level scenarios. After that, Faris Khundakjie from Intel, our workgroup chair, will talk about some new features we've added to enhance our modeling capabilities. After that, Karthick Gururaj of Vayavya will go through some of the new concepts and constructs we've added to support modeling hardware-software interactions at a more abstract level. And then Hillel of Synopsys will cover some new features we've added to strengthen the portability of PSS for system-level modeling. And then I'll come back at the end to do a quick wrap-up. So the most important aspect of portable stimulus is that it lets you capture your test intent. As you'll see, PSS is a declarative language that lets you define a set of rules that represent what's legal when it comes to verifying your design. It lets you define the specific behaviors or operations that you want to verify as a partial specification of your scenario, and lets you compose higher level scenarios from lower level ones as you go from block to system level designs. And from these partial specifications of intent and the rules defined in your system, we build up a formal representation of your test space. And from this formal representation, tools can then automatically generate tests on multiple target platforms that implement the behaviors you defined in your scenarios with the proper scheduling. So we're separating the specification of test intent, which is the model that you write, from the implementation of that intent, which can be automated by a tool. So as you'll see, PSS lets you create high coverage tests throughout the verification process as you move from block to system and from simulation to emulation to prototyping. And because you can generate these multiple implementations automatically from the same model, the overall process takes much less effort. The general tool flow starts with a description of your portable stimulus intent in what we refer to as the DSL, or domain-specific language. This is typically what is referred to as PSS and is a declarative language that allows us to define a scenario model and a set of constraints, including data constraints and scheduling constraints, between the different behaviors represented in the model. We also have defined a C++ library that's able to generate the same model. Executing the C++ code generates the same model as compiling the DSL code. Once you have the scenario model, you solve all the constraints to produce the solved model, which is the formal representation of all the legal scenarios defined by the original intent you specified in your model. The test generator takes that solved model and creates from it the implementation of the test intent on your target platform. If you're targeting a UVM environment, it will generate a set of UVM sequences and virtual sequences to coordinate the behaviors in your UVM environment. It's important to note that it will not generate the UVM environment. So PSS is not a replacement for UVM. Rather, UVM is one of the likely targets for PSS test generation. You can also generate C code from the model. It's the same scenario, just now implemented in a different language. And more importantly, if you have some of the code running in C on a processor model and some running as UVM sequences on verification IP in your test environment, the tool can create whatever hooks are necessary to still ensure that the behaviors running in different languages in your mixed environment still are coordinated to implement the same scenario from your original intent model. The solving of these constraints can be done either at gen time, where you would generate a set of tests, one for each scenario, that can later be compiled or run in your verification environment, or at runtime, where the generated code may include a generic sequence that at the right time will call into the portable stimulus tool to find out the next thing to do. Either generation scheme is valid, and tools don't necessarily have to do both to be PSS compliant, but either way you wind up with a target-specific implementation of your original intent that executes on your target platform. So what do we mean by a portable stimulus model? The first part of a PSS model is what I refer to as the abstract model, which is the specification of your verification intent. What are the behaviors I need to verify? And we specify these at the abstract level, like send a packet from here to there or do a DMA transfer. I don't want to have to yet think about how I'm actually going to implement the behaviors, because that's the realization layer. As you'll see, there's a very distinct difference between the two, and this is how portable stimulus can do what it does. We intentionally kept the abstract model at the behavior scheduling level, and in the realization layer for a given target platform, whether it's UVM or C or whatever, you specify the implementation details for that behavior. So this separation is what allows PSS to be portable across different implementation languages. A PSS model starts with an action, which is what describes a behavior. In this case, we want to do an M to D action, whatever that means. The input to the action is a buffer, which is a specialized data structure that we call a data flow object that extends from the struct type in PSS, and structs and buffers can have data field attributes associated with them. You can also have a stream object, and both of these objects can be used as inputs and outputs for an action. In this case, the stream object is an output. Actions can also have data field attributes that can be randomized whenever the action is executed, and you can also have non-rand fields as well. And you can define constraints on the action fields so that you can constrain one field in terms of another, and you can also constrain fields on the flow objects. We also have resources which are directly related to aspects of the target system that you're going to be dealing with. So in this case, it can represent something like a DMA channel, and for my particular application, I might have 4 of them. So I wouldn't be able to schedule 5 actions in parallel, and that's what lock means. There are 2 types of actions to consider. There's an atomic action, which is an action that gets replaced by a piece of the realization layer, and we'll see what that looks like in a minute. The other is called a compound action, which includes an activity, and that describes the scheduling of the behaviors that you want the action to perform. In this particular case, we have a gen action that's going to produce a buffer that will go into the M to D action. And we can explicitly bind the gen output to the M to D input, which means that both actions refer to the same buffer. So if I put a constraint in one of these actions on a field of the buffer through the input of the M to D action, it's implicitly a constraint on the output of the other action. The other key thing about a data buffer object is that it implies sequential behavior. The action that produces the buffer must complete its execution before the action that consumes it can execute. The stream object defines parallel behavior because a stream object does not get stored anywhere. When an action produces a stream of data, there has to be another action executing ready to consume that data. Buffers and streams can be bound between actions as long as the types are compatible, and since a constraint on an object in one action implies a constraint on the same object in the other bound action, the constraints between the bound actions must be compatible. If you have one action that constrains a data field of an object to be greater than 10, it cannot be bound to another action that constrains the same field to be less than 10. As scenarios get more complex, it can be difficult to manage all the flow object and resource bindings explicitly, so instead we put them in pools. As we'll see, not only do pools simplify the code, they also provide additional flexibility in describing multiple scenarios from a single model. With the addition of pools, it's still possible to bind objects explicitly, but it's not required. So instead of explicitly binding objects between actions, we put the objects in pools and then bind the pools. The wildcard symbol allows the pool to be bound to any action that is compatible with the type of the object in the pool, and this allows us to create more complicated scenarios without having to worry about the specific bindings. So here we can see a more complex scenario where we randomly select between the parallel execution of M to D and Rx, as we saw on the previous slide, and the sequential execution of M to M followed by check. Note that the binding of the debuff objects will depend on which scenario is actually executed. Depending on whether we do M to D or M to M, it's going to get its input from the gen output because that's the only previously executed action that supplies a buffer of that type. And then when we get to the check action, it needs to have an output from the pool, so it will use the output of the M to M action into the pool that then gets sent to the input to the check action. By specifying the binding rules using pools and specifying the inputs, outputs, and resources of each available action, we only have to specify the critical actions that we really care about in our activity, in this case either Rx or check. The semantics of the flow objects and the binding rules now allow the tool to figure out all the other actions that must be inferred in order to complete the scenario. This is what we mean by a partial specification enabling the creation of multiple scenarios. The last element of a PSS model is the component, which is used for grouping other elements of the model. And here you see a top-level component named PSS top by default, and this top level will instantiate a DMA component that will hold our DMA-specific stuff. The DMA component defines the channel resource and the pool to bind the resource to actions in the component, and it defines the DMA-specific actions, including the input and output and resource requirements, and any constraints on them. In the top-level component, we can also instantiate another utility component, which will have our gen and check actions defined in it. And in order to allow data flow objects to be connected across subcomponents, we define the debuff pool in PSS top and bind it to the sub-actions. Then we can define our actual test action, and again we simply specify the critical actions that we want to verify. In this case, we're using the do keyword to traverse these actions without having to instantiate them, and notice how we use the double colon notation to show which component the actions were defined in. So what's the point of all this? Well, we have the activity that defines your critical behaviors, and this is what we mean by a partial specification of the things that you want to make sure happen. And then the tool is going to infer a set of additional elements to complete the scenarios. If I include an action that requires an input of a specific type, it's up to the tool to find another available action that can provide the particular data flow object. And it is the other parts of the model that define what is available and the rules by which they interact. The instantiated components define the set of actions available, and the flow object bindings of those actions constrain what actions can be inferred. If I have an action that requires a buffer, I can only infer an action that supplies a buffer of the compatible type. And the available resources may present further scheduling constraints, since I can only infer actions that fit given the number of resources available in my system. So basically, a PSS model gives you a big box of Legos, and you can pick and choose from them to build your critical intent, and then let the tool comb through the box to find the right pieces to build the rest of your scenarios. So here's a quick example. We're executing a mem-to-mem transfer followed by a check data action, and those two actions share data through a pool. The available actions are a gen action that produces a buffer and a mem-to-mem action that both inputs and outputs a data buffer. Looking at my activity, I have my mem-to-mem action there, and it needs an action that produces the buffer, so I have two choices. I can choose either one to supply the necessary buffer to the mem-to-mem action, and because I've bound the debuff pool, any action that I infer will be bound to that pool. But if I choose the mem-to-mem action, the action requires another data buffer, so we have to keep going. There's a built-in limit to how far up you can go, or you can define your own limit of how many levels you want to infer. But what you see here is that from essentially a two-line description of our critical verification intent, we've actually produced a large number of distinct scenarios that will be tested. And if there were more actions available to supply the data buffer to mem-to-mem, the number of distinct scenarios that can be generated from the same model grows substantially. Now, I may decide that I want to do two of these tests in parallel, assuming I have enough resources to do that. So each of those mem-to-mems is going to start inferring actions all the way up the chain, and now we have lots of data moving throughout the system. And we want to make sure that these data buffers are not going to overlap. Each data buffer actually models an area of memory, and we want to make sure that we're not overwriting part of one buffer in the system while we're doing what's supposed to be independent transfer from another action. In 1.0, you'd have to manage this on your own using really complex constraints, and it quickly became very difficult. So in 2.0, we've added memory allocation, and Adnan will tell you about that in the next section. Obviously, the next step is to actually implement the abstract model on the target platforms, and this is what we call the realization layer. For each atomic action, we're going to define an exec block, and this is going to specify the target code to define the implementation of the behavior on a particular platform, and then the generator will assemble each of the exec block contents into a test on your target platform, where each behavior executes according to the schedule defined in the activities of the abstract model. The first way we do this is with a target template exec block. In this example, we tell the code generator that we're using a system Verilog implementation, and inside the exec block, I'm going to put actual system Verilog code. In this case, I'm going to be starting a sequence, and we use the double brace notation, affectionately called a mustache, to pass PSS arguments down into the template. We can do the same thing in C. The only drawback to this approach is that you need a separate implementation of the behavior in each language that you're targeting. The other way of defining behavior is using the procedural interface. This lets you define a function prototype in PSS, and notice that we have packages too, and then you can realize the function in your target language. Then you just have to manage your file so that the tool will use the right function implementation for your target. With the procedural interface, your portable stimulus model is simpler since you only have the one exec block, but you still have to do the implementation in the different target languages. In 2.0, we've added a procedural abstraction layer, so you only have to define this level of behavior once, and the tool can generate the different implementations for you.
As Tom mentioned, memory allocation is a key aspect when verifying SOCs. My name is Adnan Hamid, and I'm founder and CEO at Breker Verification Systems. We will discuss the problem that has to be solved with memory allocation, the key concepts behind how portable stimulus handles memory allocation, and how to use those concepts in applications. The problem. If we are doing unit verification at an IP level, we have to worry about how we get good addresses that will stress our IP and make sure that we don't run out of the memory resources in our unit bench. When that IP is combined with other IPs in a subsystem level, we got to make sure that we're scheduling memory in a way that two operations don't stomp on the same memory at the same time. When we want to then port those tests to the full system level, we need to make sure that memory can be allocated for SOC simulation, emulation, and post-silicon in a way that works. There are several things that tools can do to help us on this front. First, the memory allocation has to be consistent As things are running concurrently, the tool has to make sure that two operations don't schedule operations to the same addresses at the same time. We want to be able to manage the addresses that are picked so that we create interesting cases. And we really don't want to worry about using runtime allocation, which is possible, but it's slow and not very controllable. Let's talk about the fundamental concepts that we need to understand for memory allocation. We shall define an address space as a set of atoms, each having a unique address. We will consider a group of atoms to form a region. And we will talk about the notion of a set of traits that can be associated with the region that allows us to control where we allocate a region out of. We have organized address spaces into a hierarchy of types. So a generic address space is broken up into contiguous and non-contiguous memories. A contiguous address space has a set of atoms that are addressed by sequential positive numbers. This is as opposed to a non-contiguous memory space, which might, for example, represent content addressable memory. A contiguous address space is further refined to a byte addressable address space. So now we're talking about things we're familiar with, a sequence of bytes that have addresses somewhere in memory. And byte addressable memory has a further specialization called a transparent address space. And for a transparent address space, we may actually reason about the physical address of that memory. Here are the fundamental objects that make up the PSS core library. A contiguous address space component holds a set of address regions that we shall define. This is how we tell the system how much memory is available, what regions of memory are available. Subsequently, we'll create an address claim object to say, please go grab some of that memory for me. The component, the region, and the claim will all be associated via a common trait object. And by constraining trait properties in the claim, we can control which regions we will get our allocation from. Finally, an address handle is an abstract pointer to a particular claim that can be used in structures such as a DMA linked list. Let's look at how these constructs are to be used. The PSS core library defines a set of objects. Starting from the bottom here, the contiguous address space component has a function that allows us to add a region. The address region represents the available memory, or one of several available memories, and it has a size property. And a claim has a randomized size property that allows us to control how much memory we want. When we're creating a model, we might define a contiguous address space, then add multiple regions to it, maybe of different sizes. So this is suggesting that in my system, I have one region that has 50 bytes in it and another region that has 10 bytes in it. Subsequently, when we want to use memory, we can create a claim object and say that the size of my claim has to be 20 bytes, and the system is responsible for finding 20 bytes in the available regions. PSS tools must ensure that memory allocation is consistent. In our example, we've defined a first region 1 that has 50 bytes and a second region 2 that has 10 bytes, and an operation that wants 20 bytes. If we want to do 3 of those operations sequentially, that's okay. We can always find 20 bytes to allocate, free, and reallocate. If, however, we're trying to do those 3 operations in parallel, then allocation must fail. Our first operation might allocate the first 20 bytes out of region 1, second one might get another 20 bytes out of region 1, leaving 10 bytes, but the third allocation cannot get a contiguous sequence of 20 bytes. Next, let's talk about memory traits. Our system might have multiple memories, and we need a way to control which region a claim is claimed out of. Let's imagine, for example, I have a system with 3 different memory regions. But importantly, each of those regions have properties that I care about. The kind of memory, whether it's write back or write through, and the security level of that memory. We will represent those properties in a traits structure. When we create those memory regions, defining what memory is available in the system, we will define not only what is the size of each region, but also the traits of that region. Subsequently, if we come along and say we need a claim that's of size 1 megabyte, well, that claim is pretty much forced to go into this third region because it's the only one that's big enough to capture that size. If in another place we say, hey, we need an address claim and we really need that memory to be in write-through mode, then the only region that can satisfy this claim is our second region because it is the only one that is write-through. Finally, somewhere else, if we ask for memory that is at a security level greater than 2, well, again, our second region is the only one that is capable of satisfying that constraint because region 1 has a security of 0 and region 3 has a security of 0. Now let's talk about address handles. An address handle is simply an abstract pointer to a memory claim. The problem is that the absolute address of a claim might resolve at different points of the flow. In some cases, we might know it at solve time. At other times, we might want to defer that decision, say, till our toss malloc. Even if we're known before we run, we might have the absolute address at generation time. It might be determined by the linker. It might have to be determined at runtime based on some properties of the environment. Furthermore, these addresses might have to then again be remapped through page tables to address virtualization. So in the end, we really want to avoid dealing with the physical address and dealing with the abstract, and we want an abstract address that will get mapped as late as possible. So the solution is to come up with this address handle, and it's simply a way to indirect the address. So instead of knowing the absolute addresses of all our memories, we will create handles whenever we need to reference a particular address, and those handles will be resolved later on in the flow. To address this, in the library, there are a bunch of functions that let us make handles from various objects. And now, instead of creating a test case that encodes the absolute address into the final exec body, we will create handles to those addresses and use those handles in the test case and allow the conversion, the resolution to the complete address later on in the flow. Now that we understand what an address handle is, let's talk about how we can create a memory descriptor that contains such handles. Descriptors are defined as packed structures that can have multiple fields, and one of the field types in a descriptor is a sized address handle, where the size aspect of it tells us how wide the address is, and in there we find the actual address handle. And this, for example, lets us create a linked list of descriptors for a DMA operation where maybe each item in the linked list has a source address, a destination address for the DMA copy, and a pointer to the next descriptor that allows us to go build such a chain. The PSS library also defines a set of low-level operations that allows us to read and write memory via address handles or lists and structures and so on. And these primitive operations may in fact be also customized via their own traits, which are defined per design, and their meanings are not constrained by PSS. Finally, to summarize, we have looked at what are the main aspects of the memory allocation in PSS. We've talked about the address space component into which we add a set of address regions representing the available memories in our system. We have talked about an address claim that allows us to go grab a certain amount of memory out of a region. We have talked about the traits that let us control which region our claim will come from. And we have talked about the address handle, which is an abstract pointer into a claim. Why did we do all of this? In PSS 1.0, addresses were just handled as random numbers, and if you had multiple operations going concurrently, there was no way to manage and ensure that those addresses would come out to be unique. With the 2.0 memory allocation specification, the memory management is handled by the tool. Allocations are unique. The memory management is portable across platforms. We've handled address management so that they can be resolved at different times of the flow, and we are managing the lifetime of these claims such that they're allocated and freed at the proper time in the schedule.
Hi, my name is Matan. I work for Cadence, and in my part of today's session, I'll be talking about how PSS 2.0 gives you much more expressive power in describing test scenarios and how you can define scenario building blocks that are more usable and more flexible. PSS 2.0 includes multiple enhancements for describing scenarios. I'll be talking specifically about the following three: the replicate statement, default value constraints, and constraint for all. In my last slide, I'll show you how I put these together to capture a specific test intent in very concise terms. Okay, let's get started with the first construct. Tom, in his part, showed you how you can model a hardware IP, say a DMA controller, and its operations, for example, a memory-to-memory transfer, and then you compose out of these different flows. So in this example, a compound action with an activity doing 3 transfers in parallel. Now, what if you really wanted to stress that DMA controller? Imagine it has 31 channels and you wanted to schedule a transfer on each and every one of them. So would you have to reiterate the same statement 31 times? That would be quite tedious and it wouldn't reflect your intent very clearly. And what's worse, if the next version of your IP comes out with a different number of channels, this description would no longer be applicable, right? It doesn't capture your intent at the right level. This is what we have replicate statement for. What you really want to say is replicate memory-to-memory transfer n times in parallel, n being the number of channels. And that's what the replicate statement does. You can also declare an index variable and then use it within the activity block. In this example, for example, I am scheduling a transfer on each even numbered channel, right? The syntax of replicate statement has the following form: the replicate keyword and then the count expression in parentheses with optionally the index variable. I won't be talking about label arrays here, but you should definitely look it up because it's very useful. And the simplest way to explain the semantics of replicate is in the following way. Just take the activity block under the replicate and copy paste it that number of times and replace the index variable with the iteration count in each case. So the code here on the right is equivalent to that on the left, which means what you will be getting is 3 A-B sequences in parallel, and all that in parallel to that last do C. So overall, 4 parallel branches. Replicate has similar syntax to repeat, but don't let that confuse you because repeat is a true control flow statement. It's a loop. So If this were a repeat, we would be iterating through the AB sequence 3 times in one branch and doing the same in the other, right? Whereas replicate is not a control flow statement. It's not a loop. It's more like a macro, or what we call an activity construction statement. And so because it expands in place the same block multiple times, when this is under a parallel statement, you would get all of them in parallel. That's what we saw. Okay, on to the second construct that I want to talk about. Consider this quite useful building block. What this does is selects between a DMA mem-to-mem transfer and a CPU mem copy, both of which just move data from one location in the memory to another, and replicates this multiple times in parallel. So what you're getting is multiple agents accessing multiple areas in the region, multiple areas in memory, and this would stress your fabric, stress your memory controllers, possibly cache controllers. It's a quite useful little pattern. But when you want to take it over, say, from simulation to emulation, where you have many more cycles to spend, you'd want to crank up the amount of traffic that you get, and that's easily achieved with wrapping the select in just a loop. So there would be a multiple selections in each of these concurrent branches. And I'm adding a control knob here for the loop count. And observe that this definition on the right is really a generalization of that on the left. Or maybe better, the left is a special case of the right, with loop count being just 1. And it's an important special case because maybe that's the mainstream usage, maybe the mainstream usage for certain platforms, and maybe I already have plenty of users expecting that. So as I generalize this action and introduce control knobs, I also want to be able to say what they default to, and that's the default value constraint. I can specify the default with this construct and have this parallel mem access now generalized, but falling back on the simple case by default. And it becomes really important because as you generalize a scenario building block to multiple situations and for multiple purposes, possibly corner cases, you don't want to complicate the user view of the mainstream or simple users, and you don't want to break existing code. And so for all of these control knobs that are really just random attributes, you want to specify the default. Default value constraints have the following form. It's just an equality constraint with a default keyword, but really a restricted form of it because the attribute needs to be on the left and only a constant expression on the right. There's another form to disable a default. And let's look at an example to see how it works. Here's my struct with two rand attributes, utter1 and utter2. And there's a default value constraint on utter1 that it's equal to 0. I have two instances of my struct under my action. One just vanilla, so clearly I'm getting utter1 to be resolved to 0 because of that default constraint, and utter2 to randomize in the domain that's left, 1 to 3. And in contrast, for the second instance, I disable the default. So outer one in principle randomizes again in its full domain 0 to 3. And I can choose to add a different constraint. And so outer one would be randomized on the domain of 1 to 2 and outer 2 to be greater than that. Okay, now I want to tell you about a third construct. Consider the following. Here's a little building, again, scenario building block where there are 3 transfers in parallel. And imagine that for a certain application, I would want to use that, but with large transfers, right? So I can easily use this compound action and constrain its sub-actions directly from above. For example, to constrain the transfer size to be greater than 1K. But this becomes quickly impractical if the compound action or its flow becomes more complex. So now consider the parallel mem access action that we developed. It had a selection between DMA transfer and a CPU copy, this repeated in a loop and then replicated over multiple concurrent branches. If I had to reach into every instance of a DMA transfer in this more complex flow, well, I would have to know the hierarchical path to each and every one of them. And even if I did, would I really want to hard code and couple my abstract intent with the structure of these intermediate layers? This is what we have constraint for all for. Because what I really want to say is do a parallel mem access such that for every instance of memory to memory transfer, let the size be greater than 1K. And now I'm not making any assumptions on the structure, inner structure of this parallel mem access. So a for all constraint just propagates a constraint down a hierarchy and attaches it by type. The syntax is somewhat similar to for each, if you think about it, but of course for each iterates over an explicit collection, an array or a list, whereas for all iterates over all instances of a type in a certain context. So example, we have action A here with a round attribute V, and action B calls A twice. How would we interpret the constraint for all in this higher level action? It applies a constraint on every instance of A. So if we took the trouble to explicitly constrain each and every instance in the same way, we would get equivalent code. So again, if I knew the path to every instance that I'm interested in, I could rewrite a for all constraint in explicit terms. Of course, I don't always know, nor do I want to know. One more observation about for all is that it's scoped not just for a single action, but more broadly, it's scoped on an activity block. So consider this scenario where I have 2 phases, let's call them, of A and C. I want to constrain each phase separately. So I want to apply the phase 1 limit to the first block and the phase 2 limit on the second block. Let's look at graphics that will clear things up. I want to propagate this constraint on this subtree and a different constraint on that subtree. And this is really how I can massage a scenario. I can customize a scenario and direct different areas of it to different intents. Okay, now this is my last slide that I promised you a more realistic use case. Imagine that you're stressing a DDR controller in a system where there are multiple controllers and they are mapped in interleaved way, right? So first thing you would do is describe the address space the way that Adnan taught you using memtrait. So each of the regions would be tagged with the right controller ID. But having done that, for this specific test case, you could just pull out that same parallel mem access action that we developed over the previous few slides and apply a constraint on all of the allocations, right? It has DMA transfer source and destination buffers and mem copy source and destination buffers. Apply a constraint on all of the memory allocations to just pick out memory that's mapped to a particular controller. And so what started off as a completely general flow with this constraint becomes a very effective test case for our DDR stress test case. Just by directing all of the allocations to very certain memory regions.
Thank you, Matan. And now at this point, we'd like to open it up for questions and answers about the first part of the tutorial. There is more to go, and we will have a Q&A at the end, but we thought this would be a good time to stop. So if you have any questions, now's the time to ask them.
Hello, everyone. This is Faris Khundakjie, Senior Verification Tech Lead at Intel and Chair of Accellera Portable Stimulus Working Group. We will now go over a couple enhancements to provide better control over modeling. The first enhancement allows you to explicitly decide how activity termination is observed from the point of view of activities and actions that follow it. We call this fine-grained scheduling using a new keyword, join. The second enhancement allows you to influence attribute initialization in child components from their parent initialization. We call this top-down init. First, let's take a look at the existing coarse-grained scheduling capabilities. In a sequence example, if we have sequence A followed by action C must not start until the sequence completes. The sequence itself states that A must complete before B starts. It is possible that between A and B, we have some time passing or some additional action scheduled to meet any requirements that B might have. The second example is parallel, and like the previous example, C must not start until the parallel block completes. Parallel states that A and B must start at the same time and may not have any dependencies. The third example is schedule. Here, we're delegating to the PSS tool the decision to create any schedule out of all possible legal schedules, taking into account the constraint relationships and the resource relationships between A and B. Also, again, the start of C is not allowed before the schedule block terminates, which means A and B must terminate, but we don't know how to relate C to A or B. So what if we want to express that C can only start if A completes without waiting for B? For that, we introduce the new concept called fine-grained scheduling. To express fine-grained scheduling, we add the join syntax, and we have multiple flavors of join. In this example, we have some additional actions that follow the parallel or schedule block. The first flavor is called a join branch, and you can specify a specific action that has been labeled within the statements inside a parallel or schedule block. For instance, you can say join branch label X label Y to indicate that the action stated after the parallel or schedule block may only start after X and Y complete. However, there is no relationship to the rest of the actions started by the parallel or schedule block, and they may overlap the actions that are stated after the block. The second flavor is called a join select. Here, we allow the tool to randomly select any of the actions stated in the parallel schedule block, but limited to selecting a maximum of 2, and only when these 2 are selected and that complete, that we would start more actions or the action stated after the schedule or parallel block. The third flavor is more of a greedy scheduling algorithm. Here at runtime, the actions stated after the parallel schedule block must wait for the first action that complete and has been stated in the parallel schedule block. Last one is called a join none, and here the actions after the block are not related to the ones inside the block, and they can execute at any time. However, in all of these options, the activity is still self-enclosed. When the activity starts and when it ends is self-enclosing all the completions of all the actions and activities within it. Also, in all of these cases, it is still a requirement that a PSS tool or implementation must honor all scheduling constraints and all resource relationships. Back to our use case, we can now say something like label 1 parallel join branch L2, where L2 does action A and L3 does action B, followed by C. This effectively means that A and B must start at the same time. B now has the freedom to end at any time relative to A or C, but C must not start before A completes. If you replace parallel with schedule, that means there is now additional freedom on the start of A relative to B, but everything else remains the same. Let's move on to the next enhancement. Currently, we can influence the initialization of attributes in a parent from decisions that have been made by a child. So in this example, a child component that has a foo attribute and initializes it to 10 could influence the initialization of the bar attribute in the parent because the standard defines that the initialization is bottom up. However, if we wanted the parent to influence initialization in a child, how can we do that? This is where we introduce top-down initialization. We rewrite the example from the previous slide using a clarifying keyword called initUp. And initUp is strictly saying that this is a bottom-up initialization. To express top-down initialization, we would use a new keyword called initDown. And in this example, the parent's initialization of y to 9 is visible at the time the child does its initDown. So the child could influence its initialization of its own attributes by decisions made by the parent. And this is useful because, as we know, there can be many configuration decisions that are made at higher levels or multiple higher level intent decisions that are made at higher levels that we want to influence the bottom layers with. Since both now are possible, and you may use both in your description, you may ask which one wins. For that, we have a clear definition in the spec that says that top-down inits are executed first from root to leaf, followed by bottom-up from leaf to root. At least this is the idea at a high level. And this concludes the two enhancements we introduce in 2.0 for additional detailed control over modeling. Thank you all.
Hello everyone, this is Karthick Gururaj. I'm a principal architect at Vayavya Labs, and for the next 15 minutes or so, I'm going to quickly give you an introduction to the new constructs in PSS 2.0 that relate to a hardware-software interface specification. So let's start with this split that we saw, Tom referred to earlier in the PSS model between abstract model and test realization layer. So a PSS tool is going to take the PSS model and convert it, generate it to test scenarios for the specified environment, like an RTL simulation with system Verilog or an accelerated simulation with C or an FPGA or a post-silicon environment. And what you see here happening is that from a single representation of the test intent, the abstract model, the tool is able to generate the scenarios for the different environments. Now PSS 2.0 enables us to similarly specify a single representation of the test realization layer, and from that allows a tool to generate the realization layer for the different environments, so from a single specification. So what does that really mean? I'm going to take an example and cover it so that it becomes more concrete. But before that, let's take a look at the high-level summary of the constructs in PSS 2.0. So first is the procedural constructs. So I'll cover this. I'll give you an overview of this in today's this session. The second is PSS 2.0 allows you to specify software programmable registers in PSS, and there is a and why do we do that, and how does it relate to procedural constructs is also something we'll cover. The third is the descriptors, and this goes back to what Adnan was talking about earlier on memory claims, address spaces, address maps, and so on. So I'm not going to go into this again, but essentially what we can do is for DMA capable, scatter gather capable DMA peripherals, you can specify the descriptor layout in PSS with the constructs in PSS 2.0. So all of this essentially enables you, the user, to capture the device programming sequence in PSS in an environment agnostic way. So let's see how you might have done this in PSS 1.0. So in PSS 1.0, you would specify the functionality in a foreign language, which is basically C or system Verilog implementation directly. So you will specify, if you want to cover both, you'll have to specify once in C and once in SV, and then you are going to import it in PSS, in your PSS model. And once you do that, you can use that function in an exec body. You can make a call to that function, give it some parameters, and make a call. So that's basically what you could do in PSS 1.0. The exec body, the definition of the exec body or exec pre-solve, or any of the execs, they also have limitations. If you're talking about PSS 1.0, there are only a few things that you could do, essentially assignments and function calls. You cannot, for example, specify based on the return value of a function, if you want to branch, do a conditional statement. That is not something you can express in PSS 1.0. Now with PSS 2.0, so firstly, you can specify the body, the definition of the function completely in PSS. So what we are calling as a native PSS function. I'm going to look at an example in the next slide. So that should make it a little bit more clear what you can do. Other than that, you can use all of these procedural constructs also in exec definition, which means inside the exec, if you want to introduce a new variable, if you want to, or if you want to use the result of a function call to decide what has to happen next. If you want to have loops, you can do all of that. Okay, so let's take a quick look with a somewhat construed artificial example, maybe just to show you what is possible. So as you can see, here we are defining the body, the definition of the function in PSS domain itself, PSS land itself. And we do this using pretty familiar constructs to you. So for example, you can declare a variable. You can assign it, obviously, here. You can have any of the constructs that you're already familiar with in the activity statement. You can have those as well here. The control flow statements can be used in the body of the this function, in the definition of the sum function. For example, loops and conditional statements and match statements and so on. You can also have you can do break continue. This is something that does not make sense in the declarative activity statement, but does make absolute sense here in a procedural context. And you can also have return statements for a function. So what we have done here is specified the body of sum which achieves certain functionality, what we want to do, what we wanted to do. We have done that completely in PSS, and now a tool will be able to take this definition and translate that to the language of your choice, maybe C or System Verilog. Now obviously you may not want to do this for adding up numbers, but you might absolutely want to do this for specifying the configuration sequences for your DUT in an environment agnostic way. So that said, there are a couple of things you cannot do in the procedural context. You cannot have rand variables, for example. You cannot have constraints. So in short, you cannot do anything that is really the domain of the abstract model, because it is going to reflect the test intent. So that is not something you can do in as a part of the procedural constructs. Okay, so this is a very quick introduction to what is possible. So now we are going to take an example of a DMA controller and try to see how we can specify the programming sequence for setting up a DMA channel. So the data sheet says what is on the slide. We want to clear pending interrupts, set up the channel registers with the parameters of the DMA transfer, and finally enable the DMA channel, which acts as a hardware trigger and it actually performs the transfer. And finally, yeah, we can poll for a status register and just to check if the transfer is complete. So we start with the definition of the DMA component itself. So I'm going to only touch upon the parts which are maybe relevant for our immediate discussion here. So I'm going to ignore parts that are, I think, you are probably already familiar with. So here in this DMA component, we have an action mem-to-mem transfer, which in the exec body definition, you can see that there is a call to a function do xfer, which is defined just below here. And as you can see, it takes the channel number, the source and the destination address handles, and the length. And so far, I think it's probably pretty much familiar domain. So now let's see how we can actually specify the body. So first point is that you typically want to keep that in an extension of the component because that will help you separate out the design specific definition of the DMA-C from the design agnostic specification, so that you can do better reuse. So before we get into the definition of the function, there is one last step we should do, which is we should look at how registers are really modeled in PSS. because at the end of it, a programming sequence is going to specify what point in the sequence should registers be read or written, and what happens to those values. So how do they get used in subsequent steps? So what we do in PSS is, I think intuitively, if you're instantiating R inside a DMA-C, the intuition is that it has to be a component, and which is true here as well, as you can see. So the register C acts as a group of registers in the DMA controller. It is really a collection of the registers which are specified here below, and each of these registers has a component type. I have only shown one example for a DMA clear register. So this component is specified on top, and other than the component type for a register, there is also a struct type which specifies the bit field decomposition. So for control registers, you have typically a 32-bit register would be broken up into different bit fields. So you specify that inside this structure, and then you further define a component for that register that specifies the complete width of the register, and this component is finally instantiated in a register group. You can see that these components are declared as pure, so I am not going to go into details of what that is. You can also see that these are deriving from some classes like register group, redc, and pact. Again, in interest of time, we are not going to go into details of what that is. I would basically request that you look at the spec. The details are there, but the intuitive understanding that would be enough for now would be to think of redc as a component with register objects inside it, which can then be used inside the doexfer function. Okay, just one slide before we go to doexfer is just to summarize here. So for every register, we have a struct type that represents the value in the register, the bit field decomposition, and a component type that is used to instantiate the register in a register group, which is one more component. And the register group is a collection or a set of registers and possibly other register groups. Okay, so that should be enough to go take a look at the definition of the doexfer itself. So now this function here has been simplified to some extent. It doesn't use a lot of procedural constructs, control flow, or loops, match case, and so on, but all of that is possible if you want to do it. So what we are doing here is we are doing write val. So it's going to write to the int tc clear register, the value being written as f, so which will effectively clear the interrupt. So we are clearing interrupts, then we are setting up the channel registers, DMA channel registers, to set up the DMA transfer with the parameters that we receive. And then here, this is going to finally enable the channel by writing to a bit field enable inside the configuration register. And finally, we are waiting for completion of the transfer itself by polling a register, the status register. So that's it. I have not gone into details, but I hope this is intuitive enough that you can follow what's going on. The advantage, of course, is that a PSS tool can take this definition and map it easily to any environment that you're interested in. It can handle the register read writes for C or system Verilog as required. So just to complete the picture, what you are going to do is instantiate the DMA component in a top level, and also associate the register R, register group R, with a a region with an address region that maps to a specific base address. That would let the tool to completely understand the register access functions, how they need to be generated. It knows exactly the base address and the offset that needs to be used for every register. So that is the very quick introduction of what you can do in PSS 2.0 when it comes to the hardware software interface. I think we went over the recommendations. You would typically keep the register types in a separate file because you would probably want to generate it from another specification like IP exact. We did not touch upon the pure construct in detail, but it enables you to it enables a tool to specify to represent large static structures like registers in an optimized way. And all the examples use DSL, but equivalent C++ constructs are also defined. That's it for now. From me, it's now over to Hillel. Thank you.
Thank you, Karthick. Today we'll talk about system level usage. We'll talk about two things: how to reuse IP to SoC. In this example, we have a DMA IP environment, and it has a UVM environment encapsulating it, and PSS model, and we'd like to be able to use the PSS model in an SoC environment where the DMA resides. So the same PSS model can be used in the SoC environment together with the other PSS models of the other IPs. The other thing we'd like to see is how do we take the IP models of each of the IPs and compose system level scenarios with the IP models of all the IPs and get interesting system level scenarios. So when we want to port from IP to SoC, this is a mapping problem. We need to write portable code that can be taken from IP level and used in a embedded core environment in the SoC. We want to have a target agnostic, platform target agnostic model. We want to make sure that there is no target specific implementation details in that model. We want to use the solve time decisions on how that model is going to be mapped. And we want to have separation of concerns in different files. Here's an example of a target agnostic model where there's no mentioning of target specifics. It's an example of a configuration of a DMA with a compound action doing two DMA configurations. This, in the exec body, we are writing to an address and to two registers. The address that is being written to is based on an address claim that occurs in the configure action. On the right-hand side, we'd see how this could be mapped to two different target platforms. One is a target platform with embedded core. So in this case, C code will be generated that writes to those three addresses using C code, as you can see on the right here. When we map this to an IP environment, we'd like to use system verilog tasks in a UV environment to do the writes to the specific addresses, one in the memory and the other into two registers, as you can see here on the right. So to recap, the problem here we're dealing with is how do we map, how do we tell a tool which code to generate when working in the different environments. So the strategy that we take here is a means to be able to configure in the PSS model information to enable that mapping. We have developed a pattern based on using resource objects by atomic actions to use the native features in the language to do the mapping. So on the right-hand side, you see a target platform. This target platform has a DUT with 2 embedded cores and external interfaces driven by UVM agent VIPs. For each entity in the target platform, there is an executor instance. Here are our executors. There are component instances. And for each entity in the target platform, there is a matching or corresponding executor instance. For example, core 0 has an executor instance mapping to core 0 in the DUT, and VIPX0 has a corresponding UVM agent object mapping the executor to the corresponding VIP. For each executor instance, there is a corresponding resource object within a resource pool from which atomic actions can make claims for. Resource objects are associated with executors through traits. We use the same trait mechanism that we use to match address claims to region. We use that same idea to match resource objects to executor instances. Instead of hard coding the mapping, we let the solve time engine using attributes in the traits to do the mapping. This enables a more portable fashion of associating a resource object with a executor instance. Atomic actions make claims to the resource objects. The associated resource object that that the atomic action claim takes will pick the associating executor. So given that there's for each resource object, there's exactly one associated executor, selecting a resource object will select an executor. So atomic action that selects a core resource object that is mapped to a core executor will know, the tool will know from that it needs to map the exec code to embedded C that will execute on an embedded core. And so each atomic action will make a resource claim. And here's the resource claim, for example, for a UVM VIP. And that the tool will know that atomic action needs to use capabilities from the VIP and enable that mapping. And on the left side, we can see the compound actions using these atomic actions. And we also enable a way for the compound actions to influence what resource objects are selected. And that can be done through constraints, constraining instance IDs of the claimed objects, resource objects. And here we see how we provide in the language base components that can be used to define executor types. So here we have 2 executor types. One is SV based and the other is embedded C based. And the SV based one is interested in getting the right UVM path to be able to connect to the specific agent. For example, getting the sequencer from that agent. And on the embedded C side, we're interested in the core ID, the main function, so that that tool will know to map that generated C code to execute on the specific core ID within a specific main function. On the left-hand side, we show you how we provide trait values for each of the executor instances. So here each executor instance has a core ID trait, and this is how we instantiate the executor group, which has all the executor instances. Setting up the traits for the different executors, and then being able to associate a resource object with a specific executor. Here we see how we assign the resource object instance ID to be equal to the core ID. So given a specific instance ID, a specific core ID will be selected, and that executor instance will be selected. the one with the matching core ID. And here we can see we instantiate our resource object pool of 8. For each core, there'll be a matching resource object, and the tool will know automatically how to map a specific resource object to a specific executor instance based on that trait. Now we talk about how do we take the IP scenarios and compose system level scenarios. For example, we want to be able to take a DMA that reads from a DRAM and then outputs that memory data to an external interface. So here we'd be reusing the PSS model from the IP and 2 different IPs and composing a chaining scenario using those IPs. So for the system level definition, we will instantiate the different IP models and the different execution agent pools, which are associated to executors, and the memory space, the address space, to enable the system level scenarios to for each IP to get exclusive memory so they don't step on each other. When designing these chaining scenarios, which will be working on the system level, we need to provide some agreement with the IP developers. One clear thing we need is a common flow object, for example, a buffer flow object, that all the IP modelers will use. So when you integrate the different IP level scenarios into the system level, they can talk to each other. So they have a common buffer object type. We can construct any scenario with any structure. They can run in parallel, they can run sequentially, or any graph of execution and behaviors. We're going to use storage allocation so that we don't step the scenarios that are running in parallel to each other, do not step on each other when reading and writing from memory. And we want to make sure that we've covered all the interesting scenarios. So we have this buffer object, this buffer type, and the buffer type itself will do the memory claim. So every time we have an output buffer, we have a memory claim, or if we have an input buffer, we have the memory that was used from the action that produced that input buffer. So we have, for example, an abstract action called memcopy that all the IP providers will use that takes an input buffer and then creates an output buffer and makes sure that the memory is written to that output buffer. There are 3 types of actions in this chaining system that the IP developers need to be aware of. One is source. For example, you have external VIP driving ingress to memory. Other type is memory to memory. For example, you could be driving to an external VIP and then get in a loop back into memory, or a sync where you going from memory to the external VIP. Each IP has, of a certain type, have their different types of actions. For example, audio and display are sync, meaning they only have output. Touchpad and camera are source. They driving traffic into the DOT, and DMA is from memory to memory, or a CPU reading memory and writing memory is a memory to memory transfer. Then each IP provider will provide their different actions with their, of course, they're identifying themselves with the device name and using the right buffer objects based on the type of their action. And here you can see how our touchpad and camera will develop a source action, or DMA will develop a mem-to-mem action. And now we can compose a compound action called sequential chaining that will will select between the source actions, select between the mem-to-mem actions, and select a final action for sync. So you can have any source composed of any number of memory to memory, and then end with a sync action. And here on the right, you can see a graph showing how this looks from a behavioral perspective as the actions reverse. And you can see here a flow diagram showing how when this scenario is executing in runtime, what will happen is the LTE modem will write to a memory, the DMA will read from that memory and write back to memory, and then another DMA will do the same, and then finally that will find itself coming out in the display processor. And that's what it looked like in runtime when simulated. You can compose parallel scenarios using parallel replicate, using the sequential chaining scenario that was defined previously. And as mentioned, you can have any complexity of a scenario running at the system level. And to enable coverage, we define a cover group, and a cover group basically will show you that all the combinations of the different scenarios executed, where you have a source, which source you selected. Then you have your mem-to-mems. If we had only two, then we'd need a cover point for each one of them. And then your sync to determine which sync you selected, and that will be crossed with the size. And for each action that you execute, you need to sample the cover point attribute so that it gets reported to the actual cover group. And so on and so forth. This was done for the sources, you need to do this for memory to memory, and for sync. That completes the discussion on system level scenarios. Thank you.
Thank you, Hillel. Now I'd just like to take a few minutes to wrap things up. So we can group the new PSS 2.0 enhancements into three broad categories. The first, as we said, is abstract modeling improvements, which includes the storage allocation features that Adnan talked about, and the other language features that Matan, Faris, and Hillel shared with us. The second is test realization, where Karthick showed us the new abstract procedural layer to improve reuse in the realization layer, and the register space definition constructs that go along with that. And lastly, although we didn't call them out explicitly, you saw some of the new programming features we've added throughout the examples, especially templates and various collection types, including arrays, lists, and other similar types. And these new features in the language will provide even more benefit when we consider the different phases that you'll be going through in your verification process. At the block level, we're talking about mostly UVM tests, and using portable stimulus, you'll be able to generate UVM sequences based on the scenario intent you specified in your model, and the automation will assemble those into virtual sequences to give you complex, concurrent, high-coverage tests, all based on your original verification intent. And relying on the analysis that is possible from the declarative specification of your intent makes it possible for the tool to be much more exhaustive in generating these tests than you could get just from relying on transaction-level randomization or even writing them by hand. When we move to the subsystem level, we're talking about reusing stuff from your block-level models and easily assembling them into higher-level scenarios. By assembling these block-level models together, it allows us to define all of the operations between the different blocks at the scenario level and use the automation to really expose all the legal interactions between them and therefore flush out those corner case bugs that are always so hard to predict. And when we get to the full system level, we're talking about software-driven tests where we're exercising I/O transactions and multi-core interactions from the same scenario model. So since we can also now generate software implementations of some of our critical actions, we can drive the test from software without having to manually try to code up software scenarios to try and get the multiple processors to interact in bizarre ways. The automation will do that for us. So I hope we've shown you how portable stimulus can improve your verification methodology by letting you create a consistent specification of your verification intent that is portable throughout your process. By not having to rewrite your verification code at different stages of your process, this portability saves you time and resources because it's so much easier for each stage to reuse pieces from the earlier stages. This also enables the whole idea of shift left because it lets you develop much of your test content in parallel and being able to reuse your test content and scale things across your verification program. So this is a list of the companies that have been involved in developing the portable stimulus standard in Accellera. We're always looking for more help, so if your company is an Accellera member, we'd love to have you join the working group. Thank you very much for your attention, and we hope you'll take a deeper look at portable stimulus now that we've given you a taste of it. And at this point, we'll open it back up for questions.